Hi, in this example, we're going to cover simulation. And that's a really mysterious area, even though it's very prevalent in Houdini as a whole, even though there's tons and tons of development into docs or dynamic operators. The actual foundations of simulation are a bit more basic than all the modern solvers, because these are really like macro layers over everything. Here I really want to introduce all the different ways that Houdini simulates under the hood, and that'll help our understanding going forward into the more advanced solvers. So probably one of the most basic concepts of simulation is a particle simulation, and particles were in Houdini well before dynamics operators. Okay, so what I have here is I have a moving box that's shown up here. This is the target, and we just have a source point, and the source point I believe is starting at the origin. Okay, and here it's only present for the first frame. Right there. Okay, and the idea is we want all these different simulation models to have this point follow this target. So what is a simulation? And I would say that even though there's all these advanced solvers such as rigid bodies, bendy objects, fluids, a simulation has to meet two criteria in Houdini for me to consider it a simulation. One would be that it responds to its environment. So the box is our environment. The box is an external stimulus that this is going to adapt to in time. Our little point here is going to adapt to in time. And the next criteria is that it's aware of its previous actions. And that's what these dynamic solvers are for. All of these, and even something that isn't a dynamic solver, is aware of its previous time state, its previous time sample. And so with those two factors put together, we have a dynamic object. It even might seem to have its own life about it. Okay, so here's our particle simulation. So I'm going to start off by making a new pop network. Okay, so we really just want to copy this point into our particle system. And it starts off, and it's already DOPS. Okay, it used to be its own context, now it's not. And here I'm just going to go up to the source. I'm going to turn off the guide. All points, meaning source for every point, and it's only present on the first frame. And then the impulse activation, just so we don't get lots and lots of points. See, we're getting, actually that's fine because we're only having the point available on the first frame. The first frame it's a point, and after that it's not a point. So yeah, the default setup here is pretty much fine. Just switch to all points. And here it's present for the entire simulation. It's not just present on the first frame. And that's because it's holding its state in time. Okay, so now I want it to follow the target. So I'm going to put down a VOP pop. And this is the data part. Particle object solver data. Diving in. So we want to get the current position. That's easy. That's just right here. And we want to have that relative to the target position. So how do we get the target position? Because our target is connected nowhere near to this stuff. So I'm going to use a get attribute. And this will pull data from some other source. All right, so here I'm going to make a new parameter, and this will be a file path. We'll call it target points. Will be a file string, or just a string. There we go. And I'm just going to plug it in here, and it'll just get the first point, and we want the first point's position. All right, so let's set that up. All right, so we can't really get anything from the input path. So here we have to get it from PopNet's input path. So I'm going to do some backticks to make this evaluate as an expression, and op input path, which returns a path from an input node, the parent, which is PopNet, and the first index, which is the second input. Okay, so that is going to have a path to whatever is plugged into the second input here. And then I'm going to use the op syntax to turn an operator into a file path. All right, so now Houdini is thinking, okay, that's my geometry to gather, and that's right. All right, so here's our position coming in, here's our current position, and we're just going to subtract. All right, so that's how we get a difference vector from two vectors. Okay, so now let's take a look at that. I'm just going to look at the normal here. Let's make sure it's full scale. All right. And we can see the normal is pointed towards the opposite direction as our box. So I'm going to reverse that. Okay, there we go. Okay, so now the normal is pointed exactly in the direction of the box. Now we want it to go towards the box. How do we do that? Well, we could just add to the position, and that's going to create our feedback loop. Right now, we have it interacting with its environment, but we don't have anything that's causing a change on every frame. So I want to add this as a force to the particle, add this vector as a force. So first, I'm going to make it a uniform length, and that's the normalize. So now, no matter how far away the box is, it's always going to be a length of 1. There we go. And then lastly, we're going to add that to the velocity. So here's where we're going to create our feedback. Velocity comes in, velocity goes out. And it's not just going to do this on the current frame. It's going to keep looping back and forth through time. And it's going to output the velocity and it's going to input the velocity. And that's how our feedback loop, our continuous travel towards this box will be created. Okay, so whatever we do in here is going to add to that phenomenon. So all we have to do is add to the velocity. Now this is 1. It's going to really send this thing flying, so we better multiply that. And I'm going to multiply that by amp. And then let's add that to the velocity. Okay, so now let's see how that plays out. There we go. And you can see it's always seeking the box, and the particle solver knows that to update the velocity and use the velocity to send this thing flying. One last adjustment we can make before we move on is that here it's not really, it doesn't seem to have an awareness of how close it is to the box. It's always just kind of flying the right direction, but doesn't seem to have much control of itself as far as getting near and slowing down. So that's where drag comes in, and drag's a pretty universal concept in all simulations. So here I'm just going to multiply this vector. Multiplying a vector can make it longer and shorter. I'm just going to multiply this by a percentage, and this is going to actually decrease the value on every frame while the new velocities are getting added. So now we can see that it's going to be able to slow down a little bit as it approaches. Let's add a little bit more force there. And now it's a lot more responsive. Okay, so we've made a simulation from scratch. This is just about the most basic simulation I can think of out of just a few pieces. We've got our particle following our target. So now let's move on to a non-particle situation. And by the way, I should mention I've got this little node to preview our particle, wherever that is, just to make it a little easier to see. So now let's look at geometry directly. What if it can't easily be fit into a particle solver? What if we want to make deformations to polygons or volumes or any number of things? So let's build the same exact system, but directly with geometry. Let's not even use a particle solver. Okay, so I'm going to start with a DOPS network this time. And same procedure as before. Particle goes into the first input, target goes into the second input, and I'm just going to connect my viewer, and the view is locked here. Okay, diving in. All right, so I'm going to start off with an empty object. Okay, here's our object. We'll call this particle. And going back to the first frame, there's our object. Okay, now, particle. Now we want to apply the geometry. So I'm going to use a SOP geometry. Okay, so we need to give it that source, essentially. Okay, so here with the input, we need our first input. We need whatever we're plugged into our first input here. So I'm going to do backticks, op input path, the parent, and the 0 input. Okay, so now we've got the first point existing. We've applied the geometry. And the thing about the SOP solver is it is designed to take in data. It's not designed to take in objects because it is a SOP. So I'm going to use a multi-solver. And this does any number of solves. You can plug lots of solvers into that. And I'm just going to plug in one solver, the SOPs solver. And this is probably the most powerful solver because you can literally do anything in SOPs. Inside is just SOPs, full power of a SOPs network. It is a SOPs network, and it'll do that on every frame. So, and you also have the added benefit of using DOPS with it. So to me, this is the most abstract and the most powerful solver. Even if it doesn't do all the advanced features like a fluid solver or something, you can literally do anything with it. I've used it to solve vegetation and cutting parsley before, and any kind of number of weird things before. Okay, so diving in, here's our geometry coming in, and I want to apply the same system. So I'm going to do a point VOP. And let's go and copy our work we've already done from the particle. Control C. Control V. Okay. And position, and then we have our target points. And here we're going to go out into the velocity, just like we have before. So that's got the wrong connection here. So velocity is adding to this thing. Okay, and we also have to make sure that our solver is enabled. There we go, and that this is visible. Okay, and let's assign our target points again. So that'd be up, backticks, up input path, and here we have to go up 2 levels, and then the first input. And if hopefully that'll find our target, which it did. And here's our amp. So put that to something. Now, this is going to affect the velocity. See, our velocity is actually changing down here, but it's not moving at all. It's rotating. You can see that because of the velocity in the copy SOP, but it's not applying. And that's because we're not solving it with particles. We're solving it with nothing, really. It's just a multi-solver. It's just applying this operation every frame. So we have to tell it to do something here. So in our next operation after this, we're just going to add the velocity like the particle solver would. So we're going to take in the position and spit out the position because we're in a feedback loop. And we're just going to add the velocity to that. And the thing about the velocity is that it's going to be very powerful because it's per second. So we'd probably want to multiply the velocity by the space in between frames, and that'll be the time increment. Okay, so if that works, then now we should see we have our same exact system, and we're doing exactly what the particle solver has done. We've done all of this from scratch directly with geometry. Now let's abstract this even one more level. Let's not use DOPS at all. And this gets into things that we probably wouldn't ever have to use nowadays. But back in ancient Houdini times before DOPS, this might have been an approach you could use. So here I'm writing out a file and then reading the file back in on the previous frame. And you can still do that today. So let's set up a simulation without a solver and with even out a feedback loop without DOPS. Okay, so the first thing we need to do is we need to create this on the first frame to source our particle on the first frame. And for that, we're going to use a switch. Now the switch is going to allow the input on the first frame, and then after the first input, it's going to read the previous result. So I'll just make a little placeholder here. Call this previous. Okay, so all we're doing here is we're sourcing on the first frame. So we'll do $ floating point frame equals the start frame. Okay. And we'll switch that. Okay, so on the first frame, it's going to be whatever we plug into it. And after the first frame, it's going to rely on the previous result. You can see how the wires are switching here. Cool. So that's the first part. And now let's apply our following system. So I'm going to make a point VOP. In fact, let's just copy all this from our previous network. Let's copy that good stuff, because it's just SOPs after all. There we go. And this time with the op input, that path will change. So let's just rely on what's plugged into itself. So I'm going to plug the target in directly here. So it's going to be op input path of itself. There we go. Got that. We're adding to the velocity, and now we need to write this out. So we would use a file cache or a ROP output driver. All right. And let's set a path on disk. So here, I'm just going to use the current hip file directory. New folder, we'll call this IO. IO $frame number dot BGO, maybe some compression.sc. Okay, and here we could continually write files, and if we wanted to, we could just save this to disk. All right, so here I'm just going to do that. The other thing I'll mention is that we want to turn off save in background for these kind of operations. And that's because we don't want the previous file to be looking for it before it's written. Okay, so now turning off save to background, there won't be any more queued writes, and we'll be progressing in an organized way. Okay, so here we've got the point, but it's no longer present after frame 1. And that's because it's switching and we're just writing this out after frame 1. Well, that's where we're going to use feedback. So here, after frame 1, the first frame is on disk. So I'm going to Control-C, Control-V. And here, I'm just going to say read files. It's going to be reading the same exact thing as writing out. And the only difference here is we're going to time shift this back 1 frame. Before the time shift, we even had to do like $F-1 in the file name. Okay, so I'm going to clamp to the start, frame -1. And now let's see what happens. So with any luck, we should be writing to disk here. And if we view our result, we've got a feedback loop. Let's plug this in. And let's take a look at our target. And we have a simulation. So far, we've written a very basic particle operation. We've abandoned the particle and done that solve. We've made our own solver directly with geometry. And then we've abandoned DOPS and we've made our own feedback and solver in this operation. So the only thing we really haven't done is work with data directly. All of our data is currently reliant on geometric operations, points, primitives, attributes. And in this last step here, we're going to abandon that and we're going to do a pure feedback with chops, with raw data. And we can even use raw data in order to produce a simulation, even if it's not a very complex one. So here you've got the input and the target. Okay. And we're going to read that data into chops. And chops is a very old and very useful context of Houdini. It allows us to work with data directly without a geometric context. So I'll call that sim. And first thing I'm going to do is I'm just going to read in both of the geometry data. So chops doesn't have attributes. Here, I'm just going to go and do a motion effects view. It's going to be working with raw data. So here's our geometry chop. I'm going to switch to animated. And let's get the file path. So it's read input, read target. Okay. All right, so here's our tx, ty, tz of our point. And we'll call this target. All right, and here's our changing positions of the box. So what this is, this baked out the entire timeline. And we have tx0, ty0, tz0. So each of these data channels represents one of the floats that we're dealing with, x, y, and z. Okay, and really I'm just going to do a very simple simulation here. So all we're going to do is we're going to have this position blend continuously to this position. So for that, I'm going to use the expression chop. An expression chop has the ability to use feedback. Okay, so we're going to need a little bit of an extra help with this because it's a lot to cram into one expression. This expression will be done over and over again as long as we use the outgoing channel expression. So the first thing I'm going to do is I'm going to add a little parameter where we can mix in a percentage of the next position because we don't want it to go straight there. We'll call this mix. Okay. And it's going from 0 to 10. I'm just going to make another change here. There we go, 0 to 1. Okay, so here's 100% of the position, here's 0% of the position. All right, so next step is how do we read the position from our second input? Well, the current positions, that would just be $V. X, Y, and Z would be processed separately. How do we read in the next positions? Well, it's going to be incoming channel expression, then input index 1, 0, 1. Next, the channel, so that'd be current channel. Okay, so X is going to the first channel, Y is going to the second channel, etc. And then here's the time sample. So that would be current index. So we're going to blend from our value to the current index value. So if we did $value divided by 2 plus whatever that is divided by 2. See, now we get half the values of these. Okay, we don't want to do that. We actually want to use our mix. So next we're going to go $V and let's do multiplied by 1 minus channel reference to mix, and we need to enclose that in parentheses for order of operations, plus this thing multiplied by channel mix. And if that works, then this should actually blend between the two channels. Oh, and let's take out the divided by 2 here. Okay. So yeah, see, now we're actually being able to blend between these two channels. And now finally, we want to do this in a feedback way. Okay, we've read our environment data, but now we need the feedback loop. So how do we do that? Well, instead of value, it's going to be the outgoing value. It's essentially like doing that. Okay, it's like taking what goes out of it and plugging it back into it on the next frame. So we're going to do outgoing channel instead of current value. And there's no input index because there's only one output index. And then we're going to do current channel and current index, but the current index doesn't exist yet. So current index -1. Okay, and now let's only mix in a small percentage. And now we can see that we actually have a feedback loop happening. It's adapting to that. And how do we take this data out? It's raw data. How do we apply it? Well, we can use the channel SOP. It's going to take our point and we're going to apply the data coming from here. So our chop is going to be sim and then expression 1. Okay, and then we're going to read animated position data. All right, and let's try to plug our viewer into here and see if it works. And you can see even though it's a simpler simulation, it doesn't have the velocities in play because there's only so much we can do with processing each channel individually. It's still a simulation. It's still adapting to its environment. So I hope these examples really kind of dug deep into the core of what a simulation is. And now going forward into the very advanced solvers, we can both appreciate and be able to use that complexity better.